Our distributed systems project is a picture guessing game called P2pictomania, in which every player can draw and guess simultaneously. Players are rewarded for making correct guesses and also on how well they draw. In such a game, the possibilities involved in sharing resources, maintaining consensus in scores, and bootstrapping make the game an ideal distributed systems problem. Our system is configured with the help of DNSimple. DNSimple provides APIs for DNS record management, and we use it for adding and removing A records from for our Bootstrap nodes. The number of Bootstrap nodes is configurable. Nodes become Bootstrap servers until the threshold number is reached, for example 3, after which nodes are regular peers. Nodes use our DNS name to resolve the IPs of Bootstrap nodes in order to join the game network. As Bootstrap nodes can fail anytime, one particular challenge faced was stale DNS responses from caches in the hierarchy of DNS servers. To solve this, we query DNSimple name servers directly to get the IPs of the Bootstrap servers. The A records are configured with low TTL to minimize caching and hence eliminate stale responses. In the game flow, a user logs in, after which the system queries the DNS to check for Bootstrap nodes. Then, it can either set up a new room or join an existing game room. The first player in a room becomes the leader of that room. Words are randomly assigned by the game logic to all players and they begin drawing. Guesses on drawings are sent to the room leader, who checks and assigns scores based on correctness. Let's now look at how we build our distributed system and how we look at various properties such as consensus, consistency, and fault tolerance.
Raft is a consensus algorithm that is designed to be easy to understand. It's equivalent to Paxos in fault tolerance and performance. We use consensus to solve the fundamental problem of building fault-tolerant distributed systems. It involves multiple servers agreeing on values and typically arises in the context of replicated state machines. As seen in the diagram on the bottom left, each server has a state machine and a log. The state machine is the component that we want to make fault-tolerant, such as a hash table or in our case, a SQLite database. The Raft algorithm includes a leader election component and maintains a leader who orchestrates the logging on the entire cluster. Each state machine then takes as inputs commands from these logs. In our system, a log entry would include SQL commands to write to a database. Raft is used to agree on these queries in each peer's log. It ensures that if we apply a write query as the nth command, no database in the consensus group will ever apply a different nth command. As a result, each database processes the same series of queries and thus produces the same series of results and arrives at the same series of database states to achieve strong consistency. If a node recovers after a failure, the Raft algorithm takes care of replaying the logs with the SQL statements in order to keep the peers DB consistent with all other peers.
Moving on to dealing with fault tolerance in our project, there are two basic failure modes that we can have in our game. The first one is any one of the Bootstrap servers failing. The second one is any peer in a game room can crash at any time. We deal with both of these issues by first detecting the failure and then responding to it via a leader re-election algorithm called Raft, whose mechanism is similar to Paxos. As we see in the figure, the set of Bootstrap servers and peers in a game room are treated as two separate groups. However, technically, failures can be handled in the same way for both of these groups. Each group elects a leader and others become followers in the group. The node states, that is leader, follower, and candidate, are the same as described in the Raft consensus groups. When Bootstrap servers fail, their public IP is removed from the A record of our domain name. This prevents new peers from joining or creating a game room from contacting a failed Bootstrap node. For peers in the game, failure only results in not receiving game data. However, other peers in the game remain unaffected. Transient failures due to network connectivity are recoverable and nodes can rejoin the same game room without the loss of their game data such as scores. Our design can tolerate failure of less than half the total number of nodes.
There are several skill challenges we encountered when developing the game. First off, one major challenge is that we have to learn an entirely new language, which is Go. Once we became familiar with the new syntax, we found it is quite robust and easy to use, especially suitable for building DS applications. Our entire backend, including the web server, the Bootstrap server, and also game logic, was built using this new language. With this experience, we definitely became more skilled on programming in Go. Apart from that, there are also quite a few new techniques that we learned during the process. We explored the raft consensus algorithm and used it to implement strong consistency for our system. The Gorilla Web Toolkit was used for URL routing and dispatching between web pages. We also explored the ZeroMQ library for exchanging messages among the players. Although eventually we settled with using simple WebSocket for that, we still learned a lot during the process. And finally, because we need domain name service for our project, we explored DN Simple and used it for our project domain management. As for managing the team, we are proud to say we've achieved our goals on schedule. We meet regularly and we took time to properly design the code. We also divide the work according to everybody's skill set. Alright, that's the end of our presentation. Thank you.